The next presenter is Dr. Alessandro Bruno. He is co-founder and director of engineering of QuantWare, and his talk is about quantum technologies at QuantWare. Please.
Thank you, everyone, for being here. Try to be quick. I hope you were also in the other talk this morning. I'll recycle some concepts. So, QuantWare is a startup in Delft, started a few years ago with the idea of democratizing access and offering a concrete and workable path to get to quantum advantage. So, as I mentioned before, QuantWare has to do with the design, production, and sales of quantum hardware, in particular quantum processors and amplifiers. But those do not work alone. You definitely need a cryogenic infrastructure and this cabling, room temperature electronics, and control software to operate. And that's one of the main ideas that I was already anticipating in the previous talk. We strongly believe in the concept of open quantum architecture, where nowadays, at least for the superconducting approach of quantum computers, there is a very mature value chain where you can literally choose which fridge to buy, which cable to put inside, which room temperature electronics, and which software. And up to a few years ago, it wasn't possible to procure your own quantum processor, and probably even more complex was to procure your quantum amplifier. And that's when we started QuantWare, to allow for system integrators and researchers that wanted to venture by themselves instead of having to rely on full stack providers into this quantum journey. Our quantum journey, I mentioned, started in 2021 when we launched our first very small commercial QPU. We moved quite quickly because the team in Delft was already quite advanced. We moved to 25 qubit devices. We launched our foundry services, and then basically our roadmap will always be a continuation of this. There will be always more qubits and better qubits. And so we are now venturing into two fields that will be the topic of this talk, is the vertical interconnection and the algorithmic QPU, which is our way to proceed in the field, which will require, and I think we heard it over and over, you will need more qubits and better qubits. So, well, that's a quite complex and informationally dense graph. It's from a publication of a grant solicitation from DARPA, the QBI challenge that was proposed a few months ago. What you see on this graph is on the x-axis is the system size, how many logical qubits, pay attention, not physical qubits. On the vertical axis is the number of operation, which also has to do with how good are these operations. And all these points in the graph are actually the application. If this session is about application, here there is the entire panorama of what you will realistically be able to do with a quantum computer, given the algorithms that have been searched or discovered. And the problem is that this is in a log-log scale and the numbers are really big. To make it clear, because this axis, we say is actually a time, this line here is the line that means everything on this line will be requiring a month of computation. Everything above is exponentially longer. And so basically non-interesting. I mean, if something will take more, well, a month, yes, maybe a year, yes, but 10 years to get the result, and 10 years is probably already here, well, maybe not really something that will actually deliver results. And let's say there are these contours. These are contours that basically indicates the system size. These are 100,000 logical qubits. And basically at that point, when you have this kind of machine and you have a month of time, you'll be able to compute something that is probably this NMR experimental simulation, quantum chemistry, and maybe not really the disruptive application that we are looking for. As a matter of fact, for this competing call from DARPA, the interesting point is maybe this RSA 2048 point. That's basically when we will be able to decipher any encrypted message encrypted by RSA within a month. And so basically, it seems like you need to have 1 million qubits with 99.99 fidelities, so every subsystem needs to be really up to spec, and yet you will need a month to compute. And as we heard, the recurring topic is you will need a lot of qubits, and because they are not perfect, they will always have some physical error, and then you need to have error correction, basically more qubits to add redundancy, and you need to have a first layer of algorithm that does nothing else than correct the physical errors, and then on top of that, you have your algorithms. So we need to, again, solve two issues. We need to be able to have a QPU that also at small scales already allows you for error correction. We heard physical implementation with AWS, or implementation that requires a little bit of redundancy in the number of qubits, and you will need better qubits. So, well, those are a couple of slides from recent Google paper, which actually finally demonstrated that error correction is real, it works. So far it was just an idea. But Google was really bold, and final result is that if you take more than one physical qubit, so this distance 3, this red contour, means that you're using 17 physical qubits to encode one logical qubit. If you want more, you get distance 5, you use 49 qubits to have a more protected logical qubits. And they really showed that as long as you increase the redundancy or the distance of the code, the logical error per cycle decrease as expected, and even well, let's say it will be interesting in future to see if this continues. Obviously, at the distance 11, you are having thousands of physical qubit per logical qubit, but it sounds like it becomes an engineering problem to have more qubits, but there is a path to get to a machine. I mean, 1 million qubit sounds a big number, but in our graphic card, there are 70 billion transistors, and I mean, we are at the prehistory of quantum computing, but I guess technology will surprise us in terms of speed. And so I want to spend a few moments to see how QuantWare is actually approaching this. And so there will be a first part regarding, well, definitely the single qubits, the quality of the 2-qubit gates, implementation of all the subroutines to perform parity checks, preparation for error correction, and then error correction demonstrations, a little bit like what was presented by Google and their Willow QPU. And then on top of that, you need to have a path to make thousands, 10,000, 100,000, millions of these qubits. And so we will see how to get to the scale required to get to the so-called utility scale, to when we will have an advantage. So I will start by addressing the scale problem. I was already introducing some concept of this in the previous talk. let's go a little bit deeper. So this is a rendering of how a typical system looks today. This is a 25 qubit device. There is a jungle of cable, some magnetic shielding. This cable go into several discrete components, say a circulator, an amplifier, another isolator, a lot of filters. These things don't scale. And in particular, there are three bottlenecks, three challenges. One is the fan out. Normally and traditionally, chips rely on the periphery. Signals typically are delivered via PCB and wire bonds and big connectors. Those are non-scalable for their size, but also qubit at the center will have hard time to be reached. And by putting more and more control lines on the periphery that scales linearly, it will be difficult to address qubits internally without having crosstalk. Second problem is the bulkiness of all these components. Each of them has a separate case, probably not optimized to be thermalized and not engineered in a full system, but because those are discrete components, they lack the real integratability that was also the success of integrated circuits. And obviously, as you try to make more and more qubits on a single processor, your yield will decrease exponentially. And basically, your chance to have a monolithic 1000 qubit processor is basically zero very soon. So let's see how this slide goes. Oh, I will introduce our two technology that for now are in two different products already available. One is our patented approach, the vertical input-output approach. So we address the state of the art right now, non-scalable because there are a lot of bulky cables and components and difficult to go to larger qubit count. What we are working on and will be the base of the next generation of samples is a situation where basically in this rendering the fridge is the same volume, but now all the bulky components are integrated either in the cable, say the Delft circuit cables, which is another company near QuantWare, and in this vertical volume here, where there is plenty of space to integrate superconducting circuitry based on the same technology of the qubits, and the qubit residing on this qubit plane. And this rendering is actually in scale, but while here there are 25 qubits, here there are up to 1,000 qubits with all the necessary hardware, superconducting here, so the amplifiers, and the last filter necessary, and the distributed elements here. Obviously, because we have saved a lot of fridge space and optimized all the thermal links, our idea is that you will be able to connect thousands or up to 1 million physical qubits in the same fridge. I hope you've been to the show where there is an artistic mock-up of this contraption that I think I will leave for the museum. And the vision is basically that by going directly vertically and never fanning out at any cross-section of your cryostat, basically you will be able to unlock the lateral dimension where now there is space for more of these chiplets. Say here in this rendering there are 64 qubits on a chiplet, and now the space adjacent is free to put more of these chiplets, and the link between the chiplet to chiplet is actually the same link that links the qubit on the same chiplet, without losses of fidelity for these different links. One of the advantages that because you have no routing whatsoever, whenever you have if this is a chiplet of 64 qubit, 4x4, you are already at 1,000 qubit in a single module. Because you have no fan out and no routing issue, Actually, the layout is extremely simplified. If I'm a qubit, my control cables are directly next to me, and the signal are going into the board, or vertical in this case. And basically, it's a real copy-paste approach on a unit cell. And maybe one of the important topics is that I heard we are doing transmons. That's partially true. We are not married with transmons. We, in fact, do fluxonium, sonic code, cut qubits. And actually, our model is that we are actually making the scalable interface, no matter what are the qubits or the customer needs. It's done. Well, there was another part regarding new processors that are the algorithmic line and combining the qubit plane that now it's optimized to do exactly the error correction, combined to the vertical I/O. That's the way we are going to make a larger QPU available on the market and actually able to aggressively scaling, because what we heard, the next problem is scalability. The next problem is scalability. Actually, that's where we started to solve scalability, so that it's actually not going to be a problem for our collaborators. Thank you.
Thank you for your very nice presentation. Question and comments, please. Comments? Alessandro, I have some question to you. If I understand you work with transmon, yes, mainly?
I just say the opposite. Yeah.
Mainly, yes. And what about flux qubit?
Yeah.
Is it possible to construct the chip with 25 flux qubit?
Absolutely. But I sell devices, so if you want to buy one, for sure.
But what's your opinion? What is better for the final results as the computer, quantum computer? From this point of view, I can send you the laid out.
I know very well flux qubit. I wouldn't go there. They are more tunable and less coherent. And they don't offer other advantages, unless you are doing some particular.
I have another question about the resonator box. Yes, is this the box resonator? Yes.
Box?
Chip carrier, yes?
In
this one?
In the contralto?
Yes.
You still have a PCB?
This one, yes. And did you optimize the geometry of your chip carrier from the point of view to avoid some unwanted frequencies? Did you optimize?
What do you think?
Question to you.
Yes, highly optimized.
Okay, thank you very much.
The system needs to be 99.99 on every aspect, otherwise it won't work.
Last question. Very short.
Yes, will be short. Just a question about scalability, because it seems the main point here is not the size of the qubit. As you're just making a parallel with semiconductor history. It's not the size of the qubit, more is on the interconnections between the qubits. What about changing the frequency, scaling up the frequency? Is there some intrinsic limit you see, or it would be worth to go to 50 gigahertz maybe?
No. Unfortunately, dielectric losses scale like linear frequency. At 20 gigahertz, your losses are already, your coherence is impossible. While the other rule that will not change is that you will have constantly to make better qubits. So we do not know of any dielectrics that would allow working at 20 gigahertz.
Okay, Alessandro, thank you very much for your presentation. If your nice activity, thank you very much.